Hi, part 2 of the proof of the local DeMoivre-Laplace central limit theorem. To deal with the first term in this proof of the calculation for the mass function, so we have the mass function here, we did some calculation in the previous video, and here we have a first term. To deal with that, I'm going to use the fact that log of 1 plus x is x minus 1/2 of x squared and plus little o of, well, let's do big O of x cubed. Okay, log of 1 plus x is x minus half x squared plus big O of x cubed, and this is what I'm going to use for the log of this term 1. Now notice that x will play, so these small things will play the role of x. I'm going to do this separately for these two terms, and these will be the small x's for which this expansion is valid. Okay, so let's take the log of term 1, so this term here. What do we have? It's a product, and it's something in the denominator, so that immediately gives a minus sign. The log brings this exponent out in front, but I also have the minus sign, so I'm going to write this as k minus n times the natural log of 1 minus k minus np over nq, and then I have a minus, because it's in the denominator, k, the exponent comes out as a factor k, log of 1 plus k minus np over np. Okay, that's the log of term 1. And now we're going to do the Taylor expansion of log up to second order like this. So that gives k minus n, and then let's factor out k minus n, and then x, which is minus k minus np over nq. This is my x, right? So this is my x, okay, together with the minus sign actually. Okay, and minus 1/2 of x squared, so k minus np square over n square q square. And I have an error term which I'm going to put at the end, but let me then proceed to the other one. This is 1 plus x, so this is going to be my x in the other expansion, so that's k minus np over np, and then minus 1/2 of k minus np square over the square of np. And then I have an error term. So what is the error term? The error term is in the order of x cubed. What is x cubed? So x cubed is k minus np over nq, or k minus np over np cubed. Now I claim that this is not very large. So k minus np is smaller than root n of an. So k minus np, let me expand a little bit on this small. So k minus np is smaller than square root of n times an, which is smaller. It's a little o if you wish, or let me say it's smaller. For large n is definitely smaller than square root of n times n to the, well, let's just keep an. Sorry, I'm going to keep an. I'm going to keep an here. Okay, so now if I divide by nq or np, in either case my x here is divided by a constant times n, k minus np divided by a constant times n. So x is in the order of k minus np over n. Okay, and some constant, but constants don't matter for the order. So what is that order? That is going to be an over square root of n. Okay, so it's the order of an over square root of n. That's how large x is. That's how large k minus np over nq or k minus np over np is, with some constant, but constants don't matter. So if I now want to put this error term here, then I'm going to add the cube of an over root n for my error term in the first place. So an cube over root n cube. However, notice that in front I had k minus n, or k, both in the order of n. So I'm going to multiply this by n. This is my error term. Okay? This is my error term. And of course I can collapse this error term into a cube over n, because 1 over square root of n cube times n is just 1 over root n. So it's going to be a cube n over root n. This together is big O of a n cube over root n. Okay, so that was my first step. The second step is going to be to collect the first order terms separately and the second order terms separately. The first order terms will each have a factor k minus np in them. This factor here, that's a common factor. So let's add that, and also they will have a denominator nq in one case and np in one case. So I'm going to put these two terms under a common denominator npq, and I'm going to factor out k minus np at the end, because k minus np is both here and there. And then let's find out what we have. We have a minus sign times k minus n, so that's an n minus k. And because of the common denominator, we have a factor p next to n minus k. And now I'm done with this term. And then we have a minus k here, but because of the common denominator, we have a factor q. So now I'm done with that term. So now these two terms are done. Okay. And the other thing I have is the quadratic terms. So for the quadratic terms, I'm going to again have a minus sign here, and that will change k minus n into n minus k in a second. I also have two different denominators, which I'm going to make common. So for the quadratic terms, I'm going to have n square p square q square for the common denominator. I'm going to have k minus np square, because that's common in these two terms. I'm going to also have a factor 2 in front here, because again the 1/2 is common. And then what else? So with this minus will bring the k minus n into n minus k. The common denominator causes an extra factor next to n minus k as a p square. And then here I have a minus k and another minus, so that's together a plus. I have a k, and for that k I will have, due to the common denominator, a factor of q square. And that's the quadratic term, so it's n minus k p square plus k q square over this common denominator, plus the error big O of a n cube over square root of n. Okay? Now a couple of magic happens with p and q. Remember that p plus q is 1. So here I have a negative kp and a negative kq. Together that gives me a negative k. So that's what I have there. And that's nice because I have an np and a minus k, so I have one more of np minus k or k minus np, just a factor of a minus sign, so that's nice. The other interesting feature is that from these two terms I have a k times q square minus p square. But what is q square minus p square? It's q minus p and q plus p. However, q plus p is 1. So that's just k of q minus p. So those two terms just turn into k of q minus p. So that's the next thing I want to make use of. Okay, so therefore my formula is further equal to, okay, so I'm going to add here a minus sign, and instead of np minus k, I'm going to do a k minus np at the expense of an extra minus sign in front. Then I have another k minus np, so I can square that, and then pq, that's my first term. For the other term, I'm going to write an np square, which is this one, np square, and then together the k factors together just give me a plus k of q minus p. So plus k of q minus p, and I actually like better p minus q. So instead of plus k of q minus p, I'm gonna say minus k of p minus q. Okay, so these are those terms, and then down here I have a 2n square p square q square, and I have the error term big O of an cube over square root of n. Okay, this is what I have at this stage. The next step will be, oops, and I forgot the factor k minus np square, which is down here. So this is multiplied with k minus np squared. Sorry for that. Okay, let's proceed with this calculation. It's a bit tedious, but we'll get there. It's a fine asymptotic of this formula, making sure we use all that we know. So this was the last stage we had, and so let's proceed with factoring out a k minus np square, which we have both here and there. So let's factor that out, and let's write all the rest and a common denominator of 2n square p square q square. This is easy. I just have a minus 2npq for the first term. Minus 2npq over that is just minus 1 over npq. And then I have all of this for the second term. So a plus np square and the minus k of p minus q. Okay, and then I have the error term. Big O of an cube over root n. Alright, now what I'm going to do is I'm going to separate one of these guys out of the two, and I'm going to collapse the other with the np square. So I'm going to separate one of these guys, so that's a minus npq over 2n square p square q square. That's one of these, and the rest is, so plus, the rest is, and oops, and I have the, okay, let's factor out the k minus np square at the end of everything. Okay, and so what am I left with? I have an np and another p. That's the np square. Np times p. That's the np square. Then I have a minus npq, which I'm going to write in this form. That's the minus npq. And then I have the minus k of p minus q over 2n square p square q square. So this is what I have left after I factored out after I pulled out one of these minus 2 npq's. I have np square minus k p minus q and one of these guys. So that's what I get. And now you can see why I did that, because p minus q is now a common factor, and what's left is np minus k again. So this term here has one more of the np minus k in it, which is really nice. So let's make that more explicit. Okay, so npq divided by 2n square p square q square is of course just minus and then 1 over 2npq, That's the first term, and then I have the k minus np square at the end. So my first term together with this factor gives me that. And then down here I have a plus k minus np square is actually multiplied by np minus k, so in fact it's actually going to be a minus k minus np, so minus k minus np times k minus np squared, that's a k minus np cube, divided by 2n squared p square q square, and I have this factor p minus q at the end of it. And then I have the big O of an cube over square root of n. Okay, so this was the next step I wanted to do. And so now we have to collect the knowledge we have, collect the conditions we have, and I'm going to claim that this whole term is small enough to be collapsed into the error term. This whole term, by factoring out one more of these k minus np's, is becoming small enough so that it's not distinguishable from this error. Why is that? So remember that k minus np is smaller than k minus np, according to the conditions, is smaller than root n of an. So if I now take the cube of that, k minus np cube, maybe we don't need this anymore. So if I now take the cube of that, k minus np cube divided by n square is smaller than n root n cube an cube over n square in mod. Okay, and what is this? So this is n to the 3 half over n to the 2. That's n to the 1 half down there. And so this k minus np cube over n square is smaller than an cube over square root of n. So in fact this can all be collapsed into that error term. So the relevant bit, the important bit, is just this first term here. So together I conclude that the log of 1, remember we're doing the log of 1 with all this calculation, is actually minus of k minus np square over 2npq, and the second term is collapsed into the error, so big O of an cube over root n. And now if I take an exponential again to get rid of the log, so this was log of 1, this was log of 1. If I now take an exponential of this, so 1 itself is going to be exponential of all of that, so e to the minus k minus np square over 2npq plus big O of an cube over root n. But actually this is exponential of the first term, k minus np square over 2npq times exponential of the second term. Now again let me go back to what we know about an. So an is smaller than n to the 1/6. An over n to the 1/6 goes to 0, or an cube over n to the 1/2 goes to 0. So this is small. And so one exponential of small is in the order of 1 plus that small quantity. So this is 1 plus error, an cube over root n. Exponential, the exponential function, you could bound the exponential function by 1 plus twice this for small an cube over root n, which is indeed small. So that's the error term we have there. So number 1 is evaluated as exponential of this stuff times 1 plus big O of an cube over root n. So the next video is about number 2.